Okay, well, I think we're ready to start on time. Welcome again to today's colloquium, and we're very happy to welcome a local speaker, Carolina Heneka, who is going to talk about work that she's doing as in a new group here, head of the junior research group for observational cosmology. And we're very glad that you're here to tell us all about advanced statistical techniques and machine learning in the context of large-scale cosmological surveys of the universe, as I understand it. Now, Carolina, in fact, started her journey actually here. She did her bachelor work here, degree in physics here at the University of Heidelberg. And from there, she moved on to the Niels Bohr Institute, Copenhagen, in 2013, where she first became involved in sophisticated simulations of line intensity mapping, which we'll be hearing a lot about, I believe, in your colloquium today. And at that point, I believe it was mainly Lyman alpha and H alpha, the reionization epoch of the universe. You came back here and worked for a year or so with Luca Amendola, applying these techniques to understand differing signals in the intensity mapping resulting from different theories of modified gravity. And then afterward, you went along to Italy, Pisa, where you were mainly working on simulations of the 21 centimeter line, as I understand it, in preparation for SKA, for the big Square Kilometre Array telescope, which we hope will be finally arriving in a few years' time in full power. And from there, you went to Hamburg University, where you were working, among others, with optical astronomers, preparing for big projects like Foremost. And I believe you are leading one of the teams interfacing advanced statistical techniques into that forthcoming survey, which should get underway in the near future. And so after that rather long path, very happy from our perspective that you actually found your way back here to found this group. And a word about the group, I believe it was funded actually by the Volkswagen company. I mean, it is funded by the company. So the foundation, the Volkswagen Foundation, yeah. So I guess that this is a really nice juxtaposition of industrial interests and scientific interests in the end. So, Carolina, thank you very much, and take it away.
So yeah, thank you very much for the invitation and for the lovely introduction of my path that led me back here to Heidelberg and well, now to this lecture hall. So I promised to talk about the universe in multicolor astronomy at the dawn of intensity mapping and AI. So I will take you on a little tour where I start by introducing to you intensity mapping as a concept, as well as the status of line intensity mapping in experiments. I will move then the focus a bit more over to 21 centimeter intensity mapping and the currently being built SKO telescope at the radio wavelengths, and how we want to couple this type of data, intensity mapping and SKA data, with machine learning in order to really maximize what we can learn from these efforts. What sets intensity mapping apart? If you look at the scheme here of cosmic evolution, on the right is low redshift. This is where we're sitting. On the left, at some point, was the Big Bang, cosmic evolution. So with intensity mapping, we are able to look back in a 3D mapping kind of fashion, 3D tomographic way, until the earliest epoch of cosmic dawn, when the first stars and galaxies were forming, and Epoch of Reionization, when the before neutral medium during the Dark Ages, mostly neutral hydrogen, was ionized again for let's say, ionized transparent universe that we can actually observe when looking back from today onwards. So the idea is really to produce these 3D maps up until cosmic dawn in order to follow the ensemble of galaxies in their evolution and also the intergalactic medium in between sources, more generally, of galaxies. There's a couple of experiments operating and on the way. So the boxes here are roughly kind of depicting the volume of these different experiments that are being probed. I'm sorry for the flip in the redshift. So we go from left low redshift to the right to higher redshifts, and different colors are different lines. We have radio in kind of magenta, yellowish is ultraviolet, and optical infrared kind of ish. And in blue, we have, for example, sub-millimeter lines up to infrared. And what we can see already here is we have kind of a variety of different redshift probes, probed volumes. And what kind of a set apart here is, for example, the SKA in terms of volume, but also line intensity of other lines like H alpha, Lyman alpha, or oxygen lines, as will be possible with the sphere example. And if you want to have the full list, you can go here on the NASA Lambda page, and you can see the status, redshift range, and some specifics of all these different line intensity experiments. And I'm just picking out a few of them here. On the ground, we have a range of telescopes for intensity operated at the radio wavelengths. For example, LUFA, MERCAT, Hera is more optimized for statistical detection, so it's not a pure intensity mapping experiment, and MWA in Australia. The SKO that is being built and split into two parts, and I will talk a little bit about this in a few slides. We have telescopes operating or being built like CCAT for the measurement of the C2 fine structure transition that is built now and will be shipped to Chile. And we have, for example, ProMap, concentric time that also measure the carbon monoxide lines, rotation transitions. Other experiments, like for example, HATEX, are not designed per se for intensity mapping, but they can be used for intensity mapping of the Lyman line. Currently, for space, the very first experiment has been built. That's SpaceX satellite and should be launched in February. Unfortunately, I'm not sure if we can keep this schedule because of the wildfires around the JPL, where SpaceX is currently prepared for launch. So fingers crossed. But this would be really the first Pathfinder mission that does line intensity from space across roughly a range of optical, UV, infrared, and string lines. And then we have balloon experiments that are in the end pathfinders to move to space, also for CO and C2 experiments, Exclaim and TIM, that already have done some camp. So, so I've told you a lot about experiments, but what is actually line intensity mapping? So in order to measure large scale structure and evolution of sources across like large swaths of time, we can strive to detect individual sources and resolve these in the end. So I put here a field with a couple of thousand galaxies and a little high redshift Hubble source or galaxy as like a kind of the cartoon example of a galaxy at high redshift. And especially at high redshifts, we are very limited by resolution and what we can detect. So we're really at the tip of this iceberg. We can, during the EOR, detect maximum a few percent of sources. And the vast majority of sources really lies below the surface, below our resolution limit that we can reach with JWST. So the idea then is, well, we're not detecting individual objects. We're really generating a coarse, lower resolution image, but of like large maps on sky that ideally like have a full sky mapping. And in each of these pixels of these maps, we detect a full integrated emission and at a certain line wavelength. And then in more like a flavor of how we measure, for example, the cosmic microwave background in terms of fluctuations and power spectra, we are actually more, let's say, hunting for these fluctuations at different scales. in the end, this means we look at ensembles of objects and not at individual detections. And this is also what the SKA is planning at high redshift for 21 centimeter intensity mapping. We're really measuring this integrated fluctuation field instead of individual resolved objects. And here is a nice example from a theory review that we're now in Corvettes on line intensity mapping, where we have a simulated galaxy field at a redshift 5, all galaxies that could be there. If we now set a mass limit above a stellar mass of 10 to the 9.5 solar masses, roughly, we very much reduce the number of objects that we could detect. So this is kind of like a cartoon version of what a survey might be doing. When we now go to line intensity mapping, for example, of the carbon monoxide line and its first rotational transition, we see that we're detecting at a typical resolution of these type of instruments of 4 arc seconds, we're detecting kind of a, let's say, kind of fluctuation structure where like the peaks of these galaxies align, tracing molecular clouds. And for the C2 transition, we typically have a better spatial resolution in this type of experiments. And we resolve more structures. And if we go back in tendency, also kind of more sources than if you look at individual detections. So this is a cartoon version, but there's many more lines. And also redshift that we can basically scan subsequently for full tomography. And I personally like to think of this in terms of an analogy with impressionist art a bit. So let's take Monet's sea roses. So on the left, we have kind of, let's say you're in the museum, you stand like really close to your sea roses. And what you will notice in these paintings is that you have kind of very coarse strokes. The colors don't really fit together so well yet to create like a full picture of such a sea rose. You step back kind of a few meters, and you see actually the reflections in between the sea roses, where the sea roses are, and they really take shape when you kind of step back a little bit. And we're also laying this out mostly with centered on sphex as an instrument, what we can measure there. Also in this article where we've been interviewed, so you can scan the code if you'd like to have a look. And this is very similar to what we see in line intensity mapping. So here on the left, we can see kind of a zoom in similar to our sea roses, where actually I would have to, this simulation, I would have to make this even more closely stroked. We can't really see the details of these objects. And then if you look at the full map, we can see the distribution. We pick up light from sources, galaxies, but we also pick up light from in between. So this is one example here, the Lyman alpha line in these images, but of course we have like a slew of other lines that we could work also with this type of experiment. And Lyman alpha tracing the more ionized medium, what this leads to is that our spatial distribution also on large scales looks very much different. So we have here more ionized material. If we now blend over to 21 centimeter radiation, for example, at radio, what we can see is that these two fields are very anti-correlated. So 21 centimeter traces the spin flip transition from neutral hydrogen. So where we have like lots of ionized hydrogen lying here that we trace in Lyman alpha, we don't have information from the 21 centimeter line, but for example down here where we didn't have much of a Lyman alpha signal, we actually gain information on the gas distribution of neutral hydrogen. So the spatial distribution and the complementarity of these different lines is really large. Is very different, and the complementarity is very large if you want to gain like a maximum information on the underlying astrophysics going on. And we can zoom in a little bit on this. So if we look more at the galactic component, here in the center, we have some dependency on the star formation rate. In the end, then the more fuzzy structure in the IGM that escapes depends on the escape and the gas structure in the interstellar medium and the second galactic medium. And in principle, we can even have a more scattered contribution that largely depends on, for example, on the density of the medium around. And if we turn this around, we can also infer a lot of these properties from this type of maps. So for example, in Lyman alpha, if we look here at the power spectrum as a function of scale k, so this is small scales, and here on the left we have large scales. What we can see is that our direct galactic emission sitting in the center is damped on large scales due to the IGM, because Lyman alpha is a resonant line that scatters when you have neutral medium in between. So we have a certain amount of damping that tells us about the IGM. And we have this diffuse emission around sources that depend, for example, on the escape and the intrinsics of Lyman emitters. If we cross this, I had shown you these maps blending over into each other that are very anticorrelated. What we can see is that the cross correlation here is indeed negative, so they are anticorrelated. And the more ionized our medium becomes, the smaller the amplitude of the signal is, and also the turnaround is shifting. And this can be directly mapped to the distribution of ionized regions, where we have a peak at a smaller size of ionized regions when we are less ionized, and as these regions are growing and we get more and more medium that is ionized, they move to slightly larger scales on average. So we get a handle on the sizes, for example, of ionized regions. We can continue this game and say, okay, we can also correlate different line intensity maps with each other than 21 centimeter and one of the limb lines, for example, Lyman alpha and H alpha, where Lyman alpha in tendency is more scattered and more extended. H alpha is more let's say, centered around where galaxies are actually lying in our line intensity maps. You can see again the cross correlation coefficient as a function of scale k. If they're perfectly correlated, we're here at 1. But if we have a contribution of Lyman alpha that is scattered, this cross correlation coefficient actually goes down. So we can measure how much Lyman alpha gets scattered as compared to the H alpha output, and how large in tendency are these size by the scale at which this correlation goes down. We can infer how large these regions are. So I kind of like to think of this kind of cross power between different line intensity maps as a ensemble scale dependent way to do line ratios, where you learn about the ensemble of sources and their properties. And like, you don't learn about a certain scale of a certain galaxy, for example, how large is the Lyman alpha halo around this particular galaxy, but you learn about the size distribution. And I'm a little bit advocating for actually, even with the data that we have, to have a look at what we can do. So if we have a Lyman alpha power spectrum here plotted in 2D, we have here the along the side kind of scale dependency, and we here the spatial scale dependency on our map as a power spectrum. If we, for example, want to cross-correlate this with SKA, where this error will be kind of hard to do, because this is where our 21 centimeter radio foregrounds are lying. If we have a too low resolution instrument, our overlap region gets kind of tiny. So we want to have kind of more moderate resolution, so we can actually do line intensity mapping with these, for example, Lyman alpha and 21 centimeter. And that's kind of an easy way to check. But I also want to show you actually some relatively recent results of first measurements that different line intensity mapping experiments could achieve, or experiments like HEDEX that are not per se designed for intensity mapping, because it has this kind of striped gap structure. So for intensity mapping, you more want to have like a Huntington field. But you can kind of stitch this together, or in this case, it was a first stacking study, to see, okay, do we actually have these theoretically proposed Lyman alpha halos? And what Maya Liu and Nima has measured here is our surface brightness as a function of distance from the center of galaxies. If there were none of these halos, this would drop off like rapidly around the size of the galaxy, or even faster. But what we see is that we have this extended measurement of Lyman alpha brightness. So we actually, these halos actually do exist and can be measured, and even better so with a more dedicated intensity mapping experiment. Here on the right, I'm showing carbon monoxide intensity mapping, some first results from last year, where the COMAC collaboration from these CO maps could derive luminosity function of carbon monoxide, kind of bias times temperature. And then as carbon monoxide traces roughly linearly also molecular hydrogen, they could estimate here molecular hydrogen as well. Where we see kind of a trend that currently the intensive experiments are producing slightly higher densities for molecular hydrogen as these line searches appear. And well, this needs to be kind of investigated for like improved data, like for example, COMAP and other CO experiments. Of course, there's a range of interesting cross correlations. Also, I think KZ is really, really interesting with the CMB, but this hasn't been detected. I think very much ongoing work. So post EUR, the 21 centimeter signal, we also had, let's say 2 years ago, a detection from MERCAT, where this is the measurement or full map in cross correlation first, because due to systematics and programs that we plagued with for 21 centimeters, this is really the easier measurement when we cross correlate here with the Z galaxies. It could measure the cross power spectrum to determine here the hydrogen fraction. And then 23, a bit more than a year ago, the MECA collaboration could also measure from these 21 centimeter maps the power spectrum here, the first kind of large scale auto power measurement of neutral hydrogen at the rate of 4. And this is now, let's say, something we know it works, and more measurements are kind of in the pipeline to do this post EUR 21 centimeter intensity measurements. So what's happening at the EUR epoch, where SKA would like to push to for imaging? So currently, what we have learned in the last 4-ish years is that if we measure 21 centimeter intensity fluctuation during the EUR above a redshift of 6 up to like 10-ish, so this is, for example, measurement at redshift 9.1. What we can see is that these upper limits start to constrain our allowed model space or theoretical model space. So, for example, it tells us that the intergalactic medium at high redshift must have been relatively cold. So if we look at the spin temperature of neutral hydrogen, this shouldn't have been relatively cold. So if we look at the spin temperature of neutral hydrogen, and T gamma is usually the radio background of the CMB. So we always measure a signal relative to the radio background of the CMB. This could also be other radio sources, but in the standard model, this is mostly the CMB. And if now TS would be much smaller than T gamma, we see that here that we can reach like very large amplitudes for our 21 centimeter fluctuation signal. That depends on this ratio here between CMB and the spin temperature of hydrogen. So if this ratio would become, let's say, -10, this is some models up here, large fluctuations, and these are really ruled out by our upper limits. So our IGM cannot be too cold. And this realization also helps to put first constraints, for example, on X-ray luminosities at a redshift of 8 in this case, where data from the Hera collaboration was used. Very similar constraints to LOFA in terms of how they measure it, but Hera is optimized for statistical detection with their antenna setup. So in this case, these limits are like an order of magnitude lower already than LOFA at the moment. But this kind of is a race. So I think LOFA is working hard to put off limits that beat Hera again and so on. So if we look here at the soft band X-ray luminosity at high redshift of 8, what we can see is that with these upper limits, we can constrain that the luminosity should be kind of comparably high to what we see in local galaxies for local high mass X-ray binaries that dominate this band in the X-rays. So this is kind of what one might expect. Okay, we had higher redshifts, we have probably lower metallicity binaries that dominate this X-ray output. But these measurements are actually now confirming this this expectation. And of course, the more we push down these limits into this model space, the more we will learn then about this ensemble of high redshift sources. And well, okay, if one like pinches an eye a bit and turns this around, this also fits well to lower redshift measurements, where this measurement of the X-ray luminosity would be lying somewhere in this model space here. So our error bars are still large, but we're starting to improve on things. And well, next step. So this was the precursor instruments to the SKA, the Square Kilometre Array. And this is most that is to know there about the SKA in one slide in terms of the instrument. So what you have to kind of take away from this talk is that we have an SKA mid instrument and we have an SKA low experiment. One is in South Africa, the other in Australia. And the SKA mid is the instrument with large dishes built to probe the post-EOR signal of the 21 centimeter intensity, meaning we probe neutral hydrogen that's more confined to radio galaxies. And SKA low is really probing the epoch of reionization and cosmic dawn above a redshift from 5 to 8, up to, depending on the sensitivity estimate that you use, something like 20-ish, maybe. And it's really designed for imaging and not statistical detection. But of course, the first step will be statistical detection. And we have here large dishes, roughly 200, that are being built. And they include, though, the 64 mega dishes that already had been built, and something like roughly 100,000 low-frequency antenna for SK111. So this is an image from Mercat and the continuum. So here all the background dishes, this is Mercat dishes. And this is a screenshot taken from the synchronization video, where actually the first SKA mid dish was synchronized with the rest of Mercat. So then the next step will be to also, they already detected the pulsars, but the next step then will be to ramp this up for 21 centimeter intensity mapping as well, beyond other science cases, as I mentioned, also pulsar searches. And then, in case you missed it, this was announced in September, but the data was taken in July. This is the first roughly 24-hour tracked image from SKA low. This is the very first antenna that was being built. This is not a simulation or like a kind of scheme anymore. This is actual SKA low antenna that are observing. They're also observing during the day, but I mean, also during the night. So, and this is the current setup that was installed until the end of December, roughly 2,500 antenna in 6 stations. And this image here was taken 2 stations, S8, 6, in 2 polarizations, vertical and horizontal polarization. And yeah, we can see the Milky Way already for these 2 stations, moving across Magellanic Cloud. We start to see kind of a quasi-extragalactic background that appears. The sun is moving along. And of course, so this is only 2 stations. So in the end goal in the next 2 to 3-ish years is to ramp this up to a couple of 100 stations for the full SKA layout that we will use for science commissioning and the first science proposals that I think are already gonna be due in like 1 or 2 years. So this is moving actually fast now, since the first stations have been built. It's been a long effort, but now it's really moving fast. So here I'm showing you basically similar pictures as at the beginning. So we have here kind of us as observers sitting in the center of this cone, and 21 centimeter intensity mapping really aims to probe this full volume, roughly scaled with volume of the observer universe, which means in the end, we have a radio interferometer that we're correlating like 100,000 antenna. So we have data volumes that are ramping up, and that will reach something of a few like terabytes per second. You measure lots of modes if you look at it in terms of like Fourier and power spectra. But we also plagued a lot by foreground noise and systematics. And the signal itself, even theoretically, is relatively, it's not easy to model analytically. It's very non-Gaussian. So are we actually up for the challenge of analyzing this data in the next few years? And it's moving fast. And can we use modern machine learning for this? So just a quick primer of why I think we can use modern machine learning for this. So this goes back to experiments in the 60s, actually, I think, where the lab of David Huber and Thorsten Wiesel was testing a neural response to visual stimuli. And they discovered that there's basically different layers of neurons in the visual cortex of mammals or animals. They actually tested this with cats, which is a dark side to that kind of cats and dogs classification that neural networks do all the time, kind of, as like a poster example. But well, so they discovered that first there's like simple cells that pick up shapes, and they hierarchically construct these shapes together to form the concept of the cat. They're not forming like an image of the cat. They're forming like a notion of cat, going from these simple shapes and connecting with each other. So they learn representations of objects, for example, and they do it hierarchically. And this concept was picked up in the 70s for example, convolutional neural networks, where we have these different layers of these neurons that connect hierarchically and are then able to form something like a concept of object representation. And representation in the end means we have something that's relatively nonlinear and non-Gaussian, because actually an image of an animal is a very nonlinear, non-Gaussian object. And we have high dimensional correlations that go here over like different layers between different parts of this kind of a neuron cascade. And this is also what we have in astronomy. We have different representations that can be tricky. So the same thing, like a galaxy, can look quite different, or different things, like a galaxy and an AGN dominated spectrum can look relatively similar here from SDSS. We have large volumes of nonlinear, non-Gaussian imaging or structures. We can have high dimensional correlations. Structures tend to form hierarchically. And all of astronomy basically is like a huge inverse problem, where we kind of look up and observe, but we need to deconvolve this with noise that is perfectly unknown usually. So, so if you have an algorithm that can basically go backwards and forwards and convolve or deconvolve inverse problems, this is great for all of them. And just to showcase here what is actually the difference between, let's say, the CMB that I mentioned earlier and line intensity maps that the SKA will do. Here we have these kind of 3D maps of 21 centimeter, and we might want to measure something like, okay, what's the background color? It's kind of like in an image here of a duck. Or for SKA mid, you want to look at radio galaxies, deconvolve them and measure properties of these objects. And we kind of want to detect some kind of object, like the duck here. So this is, as I said, a representation that's very non-Gaussian. If we randomize the faces here, we get something like a Gaussianized duck. So these two images, they have the same 2D power spectrum, or also the same average power spectrum, but these are kind of very different images. We have much more information in here, and here we cannot really tell anymore, like how large was the duck and what was background fluctuations. This is kind of largely the case for the CMB, where we can use a Gaussian summary to describe these fluctuations, but it's not true for 21 centimeter intensity mapping. So this comes together with what networks can actually do for us. They can actually go beyond this kind of Gaussianized image of a duck and detect these structures. And one example for SKA mid was the SKA data challenge, the second one, where we have a large cube of radio galaxies simulated that are relatively low in signal to noise. And the goal is to deconvolve these galaxies and measure properties like flux and the typical size in H1. And what we saw in this challenge is that network models, even like a relatively simple one, like a 3D UNet, can deconvolve these images really well, even in as like a 3D structure. So this is a 2D image, but you have to believe me, this is in principle a 3D structure that could be deconvolved. And if we look here at the error, for example, of the H1 size measurement in arc seconds, here the dashed line is the beam size. What you can see here is the blue dots. This is the best performing model, which was a network-based one. And this beats kind of long running detection pipelines by a little bit, depending on the size. Not always. It sometimes fails. For example, for very bright objects, the machine learning pipelines tended to fail sometimes. It was a blind challenge because there was not many of these objects in the training data, which is like a very bright object is usually the easiest one. So we kind of have to be careful when we apply these things. For the SKA low part, where we're more hunting for like measuring these fluctuations instead of properties of single objects, we have, as I said, kind of this non-Gaussian, non-linear signal, and we don't really know how to write down the statistics of these fluctuations because they are not Gaussian. We don't know what's really the likelihood for this. Or even worse, it was shown that if use MCMC, classical Monte Carlo sampling, to constrain the parameters of these fluctuations. First, one run takes months and months if we have like these 3D tomographic data. And even if we test this without any noise, we get biased results. And this is because for MCMC, we're writing down the Gaussianized likelihood, and this likelihood is very much off from the actual signal, or too much off, so we get biased parameter constraints. So, and just to show you again what kind of cube we're actually talking about. So this is scrolling through redshift here, and here the reddish to yellow colors, this is an absorption against the CMB, and the blue part is an emission against the CMB. And what we can see is that first we have kind of a cold medium, which is heated up to emission, where at some point these black areas get larger and larger, and we are entering the regime of post-era, where the medium is ionized, around a redshift of 5 to 6-ish. Point-to-point constraints from the Lyman alpha forest mostly. And for this type of 3D object, we now really, mostly also because of this constraints that the classical parameter estimation puts on us, we're moving as a community more to likelihood tree inference with networks in order to measure these fluctuations. We have these 3D structures. We don't know the optimal summary for this because it's only non-Gaussian. So we need some way to compress this data without biasing our parameter constraints. And we need a parameter estimator that is fast enough to estimate actually astrophysics and cosmology from this type of data. One way is to say, okay, well, the first thing these instruments are going to measure anyway is going to be power spectra. Because then we're binning the data, we have more signal to noise. So this is the first thing, to be honest, that we will get. So let's start with that. So we analytically estimate a 2D power spectrum, a fixed summary, which is Gaussian, which we know is kind of wrong, but hopefully not too wrong. So we estimate this, and then we use a neural density estimator to treat our interactive likelihood. Why do we do this? We don't really know the covariance of these things. So we learn this on the way with this neural density estimation. And here's 2 examples. So at the left, we have high redshift, 12-ish before Epoch of Reionization. At the right, we have kind of a 2D power more towards the end of the EOR at a redshift of 7. And we really see this is clearly involved. This has information content for us and for the network estimator of the likelihood of posterior. And here, what one of my students, Heneka, could show, the work that he is leading, is that if we take this 2D power spectrum as our summary, we apply neural density estimation based on normalizing flow. We can, for example, reconstruct for different fiducial models, the reionization history of neutral hydrogen, where we go from neutral hydrogen up here to ionized to an ionized medium on here. And we can put trustable error bars on this. and really directly reconstruct this functional form for the EOR history. But well, I told you, okay, this is non-Gaussian. So what about the summary that we put? So let's take the next step. So we also want to find an optimal compression or an optimal summary of this type of data that then we can couple, for example, from before with the neural density estimation. What we found to work really well is the base flow framework, where we now have a compressor network up here that takes these type of 3D data as an input, forms a summary, and then we can calculate the model parameters conditional on the summary on the data, which is exactly our posterior for our parameter estimates that we aim to do. And what we saw, what I think is really, really interesting, is that if, let's say, we take the cube up here, which is actually no noise in the cube, like our assumption that we can subtract all the noise, we have all the information, which of course is not true. But if we use this scenario, what happens is that the summary vector that we're guessing from like the parameters that we know in a kind of, let's say, Gaussian scenario, or a very simple scenario, these summary vector parameters are not really moving. So the compressor is not really adjusting them to our like best guess. So we don't gain as much from this compressor here. But as soon as we add noise, what we see what is happening is that the summary vector is moving away a lot in order to make sure that we have an unbiased posterior constraint. So this means if we want to have an unbiased parameter constraint, we don't want to be over or under confident in our posterior contours, we need to actually adjust in the presence of noise our summary. And we need to learn this because we cannot fully model it. And just to show you this in action, and yeah, I wanted to mention, of course, we did a range of performance validation. So the beauty of this is because we can evaluate so many, basically, each of these images is an MCMC run, and we can do this tens or 100,000 times, which means we can actually see if for enough like samplings, we are recovering the prior again. So this is so-called simulation-based calibration. And this tells us if our posterior contours are too large or too small or just right. And we find they are just right, roughly. They are actually slightly underconfident. The contours are a little bit larger than what is the optimal estimate. But this is fine because, well, we know we are slightly underconfident because we don't have infinite kind of information and training data, but only slightly. So if I run this, we can see each of these frames is a full Monte Carlo run, where we, for example, have different fiducial models that are reflected in our light cone here, different amounts of omega matter, ionizing efficiency of galaxy that is steered, for example, by the escape fraction, or the typical softband X-ray luminosity at high redshift. And well, there's some more things to do about this because, well, we're compressing the data, we have an optimal summary in principle, and we do our parameter estimation. But there's, let's say, I mentioned we were slightly underconfident. There's still lots of improvement that we can do in the way how we jointly train these two networks and how we really optimize our loss or cost function. That is the goal for our network to learn. So in the end, this means we can still improve a bit our parameter estimate. And this is also what Tom, my student here, is working on, the really optimal SPI framework for the SK. And going beyond inference. So for now, we already were focusing on always the inference part. But what if we want to ask, okay, what's really inherently the optimal representation of this type of data? Not the summary specific for the task of inference, but what is like inherently the optimal representation? So this has a dimension of like 1 billion pixels. How large does this representation has to be, and how correlated basically, which we can learn with the network in order to represent all the physical information in this high dimensional space. So we're compressing again, but we're leaving a little bit more wiggle room. And actually, if we learn this in a supervised fashion, which means we tell the network, okay, this is this parameter, this is this data, and we do this for many, many examples, what happens is that we have kind of a hard time in transferring or generalizing, which means that, for example, if we have an unknown amount of noise and then we show it, we might get biases as well. So we can mitigate this a lot by using self-supervised learning. So we train our model now without using labels in an unsupervised fashion. And here's an example. So for example, we might show low resolution light cones that don't have any noise, with kind of the same or similar set of physical parameters. And we train on this. And then we ask in self-supervised, we train this in a self-supervised fashion. And then we test, okay, if we now go to a higher resolution, we have more model information in the data, and we even add noise on top that the model has never seen. Can this generalize? What is happening? But usually you would say this is impossible. Like your model doesn't have noise in it. It has a totally different resolution. And as I will show, it even has like different knowledge about physical parameters. So how should it be able to get unbiased constraints? The way of self-supervised training, or the flavor that worked best for us, was JEPA, a joint embedding predictive architecture. If you're interested, I can also talk about this afterwards. Where we, as I said, pre-train a vision transformer twin for this JEPA kind of framework on this low resolution. And we totally freeze this model. So we don't change this optimal representation that we asked for from JEPA anymore. And then this frozen model is evaluated on incoming data that is more high resolution and has also noise on top, which our previous model didn't have. And then as a test case, okay, we use inference as a task to see, okay, how well or bad is this actually doing. And what we find here first for the low resolution data set, this is a similar parameter set as before. So we have two cosmology parameters, two here E0 LX parameters for the cosmic dawn, typical galaxy properties at high redshift, and two typical EOR parameters, like the ionizing efficiency of galaxies. And what we see, our summary that's trained can infer parameters as well, and also a benchmark that's trained supervised. So this one sees a lot of this low resolution data and is trained in a supervised fashion. In both cases, we cannot learn anything here about this test parameter, which is the one that matter mass, because the resolution is so small. The effects of this parameter are really at so kind of low scale that in the low resolution data set, we're not resolving these. So that's why we just get a mean estimate here. We don't have any information. But if we now go to the high resolution data set plus noise, we again train supervised. So this one only sees this data set. It doesn't know about the low resolution, and it learns these parameters. But also the pre-trained model learns this, or can correctly constrain or regress these parameters. Because it really learned the underlying representation optimal for this type of data. It doesn't care if you change the resolution or if you add noise to it. It still gives you the right parameter estimate, and it even does so for a parameter that in principle it hasn't seen in the low resolution set. So this is really true generalization of your model that you use for inference. And then as the last example, I also would like to show you, okay, kind of the inverse approach. So we have this like kind of large volume of data. We need to model it. So, okay, we can make our inference better, but we can also say, well, what kind of hinders us really is the simulation cost of more detailed simulations. So can we evaluate this with modern machine learning? And are we up for this challenge? So, well, can we really emulate this whole 3D simulations with networks? It seems to work quite well with diffusion, where we go from a noisy kind of realization to the images. And in training, we go backwards from an image to noise. So we learn this mapping between noise and image. And we do this for our EOR kind of realizations. And we can see that we can generate different fields at different fraction of neutral hydrogen. And we can do so conditioned on one parameters, which is more like a simulator, let's say, classically, where we condition on parameters. We get the same pixel distribution, but maybe we get a different field. Or we can actually constrain on fields like from the dark matter field, and then we want to generate really the same field that we expect based on the dark matter field. So these simulations can be very fast and can also be produced in a conditioned fashion, both on parameters and on fields. And just to wrap this up, as kind of outlook, of course, I talked a lot about light intensity mapping, but also I think other fields of astronomy profit a lot from this type of techniques because they're facing in the end similar challenges, where not only large-scale surveys but also high resolution, for example, imaging and spectroscopy, profits from, for example, being able to extract more and less biased information potentially. And one example is the Euclid Space Telescope, where we have a high fraction of blended galaxies. So to get good and unbiased photometry from these sources, we need to be able to disentangle, for example, a very irregular fuzzy galaxy from something that's maybe like a spiral or a relatively easy to fit spherical galaxy in comparison. What we found here is that firstly, at the top for photometry, we can measure the photometry of blended galaxies, both, let's say, the more bright one and more faint one. We did different tests, about an order of magnitude or two better as compared to our baseline fitting. And what I think is kind of the impressive part here really is if we look at the bias, so this is 6% bias, this is a 40% bias. So when we look here at this kind of greenish line, this is irregular galaxies. And in kind of baseline fitting source extractor, what happens at this example is that we get very much bias for irregular objects. The network doesn't really care. It learns a representation also of the irregular object in order to constrain photometry and also actually masks of these objects. And as the last challenge, classification for large surveys, here together with Nicola Napolitano, I lead the infrastructure working group for data-driven classification of spectra, where we have, or planning to have in like a year or so, 40,000 spectra per day incoming with formers in Chile, put on the 4-meter Vista telescope. And we already developed a probabilistic multi-classifier that can classify the spectra in a few seconds and then distribute it to other pipelines and survey science cases. So the performance is already better or equal to template fitting, but we see some interesting things. For example, there's basically no misclassification between stars and quasi-stellar objects. And we have a little bit of disagreement on how you sort different subclasses of galaxies in AGN as compared to like a baseline SDSS fitting. And lastly, we can also use this for a fast anomaly detection on the fly when the spectra are incoming. Here we tested a setup where we encode incoming spectra to a space of eigenspectra and coefficients. So you can use the reconstruct full spectra, even beyond the observed spectrum in gray here. And we can, for example, correlate this to look for anomalous objects. So this is the last thing I wanted to show you. And to wrap this up, I really want to stress that both galaxy surveys, for example, and also multi-line intensity mapping can really go hand in hand to map these 3D structures, both like characterizing objects and their properties, but also learning about the ensemble without information about single objects. So I think this really goes hand in hand for a full picture of galaxy evolution across time from today up to cosmic dawn. And I hope I could give you a glimpse that deep learning and artificial intelligence, in a broader sense, can really help us in this cycle of scientific exploitation of this type of data, from inference observations to simulations and modeling. And thank you very much.
Thank you very much indeed for that glimpse into the future. I think we have online people. If you would like to ask questions, please type in to the chat. And let's start with the audience here. If there are students, maybe you'd like to kick off. Yes.
Thank you very much for the talk. Could you go back to the confusion matrix? Yes. Could you zoom in? Like, I do not see the labels very clearly.
What do you want to know about it?
Yes, my question is, I see that there's some confusion absolutely at the bottom left, and at the top right as well, there's some. I just want to know what we are confusing against.
Okay, so you have stellar types here, different ones, and you have galaxy subtypes here in that corner. So you have more confusion. So there's some galaxy subtypes that are often classified as NIN in SDSS. So for example, what the algorithm is doing, it puts some of these NIN ones in different in other subclasses. So it says, okay, I know what kind of subclasses is from the other ones. So it draws the lines a little bit differently between the classes. Then, for example, the SDSS template fitting does. And I don't think this is necessarily something bad, because in a data-driven fashion, it sorts them in a different way than the template fitting does.
And at the very top?
You mean up here? Or
yes.
So this is star K3, K5, K1 stars. So it's slightly sorts them differently. But this is still, so this is 3% of the sources that are sorted a little bit differently. But this is still a relatively good classification performance.
Thank you.
And yeah, question is if we trust the baseline 100%, actually.
Okay, I think we've got time for maybe a couple of questions. We're running slightly late, but if you'd like to go ahead, anybody? Looking on here, nothing here. Can I ask a question? You showed these really nice simulations of the H1 distribution of the H1 power spectrum with time. You also showed some LOFAR data, I think redshift 9 or something, on H1. And you mentioned it was too hot or too cold. I couldn't remember. It was, yeah. I mean, are you, yeah. So what sort of temperatures are you talking about there for the H1 in this? And what does hot and cold, because H1 could have quite a large range of temperatures in principle.
So we're ruling out anything, I think, if I remember right, below like a couple of hundred millikelvin in the power spectrum. So this is kind of millikelvin squared 10 to the 6.
Okay.
If we say we dominated by this,
okay, so basically it's pretty fairly warmish H1, and I just was interested to see how that compared with the simulations you were doing.
Yes.
You know, whether that was sort of.
So we're actually expecting it to kind of, because this is basically what exactly is happening here. So here we have like 150 millikelvin. I can run this. So this is like 150 millikelvin, for example. And this is really then warming up, actually.
Here, millikelvin is the antenna temperature you're measuring, right?
This is the offset brightness temperature relative to the CMB.
Right, yes.
Yes.
Okay, so okay, I was getting confused with physical temperatures of the H1. So when you're talking about this, you're talking about the signal into the telescope, actually.
So yeah, so what we're actually measuring is relative to the CMB and the spin temperature, which is not like a physical per se measured temperature. So we measure really this offset. And
so yeah, that is a physical temperature. Okay, so maybe we can continue afterwards. That's an interesting point. I probably need to educate myself. Keys, you have a question.
Yeah, I also have to educate myself because I'm not really sure if I understand that movie, this one by Leon Ribot. So what is the X, Y, and Z axis of that box? What do they mean?
Okay, so this is, yeah, before it's kind of funny to do it in this way because then you kind of see the model flowing past you. So basically up here shows you the redshift of this plane at the top. And then let's say the square up here is like the spatial kind of slice. So you see basically spatial slices kind of moving down with time. And the time you see up here is the time of the top spatial slice.
Okay. So you're just moving through the column. So the column is actually much longer than on the screen. It goes all the way down and you're just scrolling through.
Basically we're scrolling.
Okay. Yeah, I was a bit confused because I saw like two independent time axes and like the vertical axis and then the Z. It was like as if they were independent, but now I see what you mean.
Thanks.
Okay, but I mean, as a matter of fact, the absorption characteristics will, of course, depend on the physical temperature of the H1 gas. So that has to come in there at some level into the simulations. And
so basically, the minimum we get here is due to the coupling of our spin temperature to the gas temperature.
Yeah.
So when we're like, let's say at the very beginning here, we're black, we're basically at a CMB because we don't have the right kind of density and temperature to really couple to the CMB, to the gas temperature. But we couple to the CMB, therefore, at like the tail of the black body spectrum.
Yeah.
So then, but then when we have like a bit more heating, we reach higher temperatures, a bit more gas density. What happens is that we couple here our spin temperature to the actual gas temperature, which is basically exactly this epoch here. So the lower the gas temperature that you couple to, then naturally, the lower it will be the signal in our model that we measure.
Yeah.
Oh, that's a great point. Yeah.
We'll maybe discuss further on that afterwards. I think there will be an opportunity afterwards to talk further with Carolina on some of the other slides. But I think we'll have to slowly wrap up now. I don't see any online questions. So if I may just, before we thank Carolina, if I may just put up a couple of announcements. So the first announcement, as you should all have got an email from Catherine asking everybody in each institute to send in to their institute representative suggestions for speakers for the next semester. Just to remind everybody, once we've got those suggestions, we'll collate them in a single list from all institutes and then send them out again to the institutes where you can vote, not voting for your own institute proposed speakers. So it's the Eurovision voting scheme. And then that comes back to our committee and then we'll rank them and then we'll choose the speakers on that basis. So please do participate this. You really have a great chance to make suggestions and I hope that everybody will participate in this exercise. So, and then last announcement is just to mention next week's colloquium by Sylvia Ekstrom, who is coming back and talking another. Of course, Sylvia is a very, very established, one of the main workers in the field, working on stellar evolution, and she's coming to tell us about massive star evolution and the status of the field as she sees it. So do come along for that. So now, Carolina, thank you very much for giving us your insight and overview into this really what I think is an interesting, very important addition to observational astrophysics. And indeed, we wish you great luck in the future. It's going to take off, I have the impression, with all these big observatories coming online in the next year. So thank you very much, Carolina.